what does it mean to encode? So if I have some piece of data, let's say it's the number. So we're going to start with natural numbers. So let's say it's something like 0, 1, 2, 3. We want two functions. So we want a, let's say, nat to church takes a racket natural number and returns a lambda calculus term, which is the encoding of that number. And we also want another function that goes the other way, which is church to nat, that takes a church encoded number and returns the corresponding racket number. We must assume that the input term is an encoded number. And so what I mean by that is there's lots of lambda calculus terms, right? Things like, for example, the omega term. So is the omega term a church encoded number? Well, let's find out, right? It's not one you're never going to be able to reduce the omega term to anything. So, but a kind of a bigger issue here is that we're going to start by taking numbers, writing this function nat to church that's going to spit out a lambda calculus term. That's going to be the encoding of the number. And that encoding, that encoding function of nat to church, it's not an injective function. There's lots of lambda calculus terms that are not going to end up being the encoding of any number, right? So we're not always going to be able to take some lambda calculus term and turn it back into a natural number, but we're always going to be able to take a natural number and turn it into a lambda calculus term. And if we started with a natural number, we should be able to round trip it, right? And so one thing I do need is I need to know whenever I, for any number, for all natural numbers n, I need to know that church to nat of nat to church of n is equal to n. All right, so that's one property that I need. I need to be able to do this sort of round tripping property. All right, and so, there's some interesting stuff here. If you kind of get deeper into this field, these two things have some relationship to each other, but we'll try to keep it more intuitive for now. Okay, so the encoding of the number n is a function that is basically says, you give me a function f, so it's lambda f, and then I will apply that function n times to some argument x. All right, so if we think about it a little bit, this is essentially a function that is f compose n times, right? So what does it mean to compose the function f 3 times? Well, so what would be f composed 3 times, or sort of the natural number encoding of 3? It would be lambda f, and then lambda x, and then it would be f applied on f, applied on f, applied on x. And it's not that the encoding is f compose 3, right? It's that the encoding is basically you give me an f, and then I return back a function that calls that function f 3 times, right? And so this is a little bit abstract, but let's just start by looking at some examples. So let's take, this is a quick answer that I did in class today. And I asked, what is the number here? And so the answer should be that we just count all of the f's. So we got 1, 2, 3, 4, 5, 6, 7. Okay, so 7 f's. What about this one? Lambda f, lambda x, and then x. Well, here we don't see any calls to f. It turns out this is actually the encoding of 0. So that's what it would be to do f 0 times. Okay. And then I say something here, which is basically that, let's take this term right here. So we've got, a fairly complicated term here that's actually got this beta reduction we can see on the outside. And if I just beta reduce it a little bit, well, now I've got some more opportunity for beta reduction. So let's do it some more. And now I'm eventually at a normal form here. So here we can see I've taken this top level term, and through a number of beta reductions, I've got it down to lambda f, lambda x, f, f, x. So what number is that? It's the number 2. And it's important to recognize that this thing computes to 2. So it kind of is 2 in the sense that it evaluates to 2, right? And because of the Church-Rosser theorem, if we get to a final result, right? So here, this is a normal form, right? So a corollary of the Church-Rosser theorem is that normal forms are distinct up to alpha renaming. And so we know that basically it's fair to say that this thing computes to 2, right? It can't compute to anything other than 2 because the Church-Rosser theorem says that any path that we take, if it ends up in a normal form, will now give us this thing, which is the Church encoding of true. Okay. So now I've told you about the encoding. I've insisted that the encoding has this very specific property that the encoding of the number n is a function that takes f, so it takes some other function f, and then returns f compose n applied to some x, right? How do you know, like, how does that have any meaning, right? There's nothing that stopped me from making up some totally different encoding, right? This is just one potential encoding, but it turns out it doesn't actually mean anything until, so I talked about the fact that I have this nat to church, right? I also need to be able to take things that have been church encoded, and I need to be able to turn them back into natural numbers. So I need to be able to round trip things, which is kind of a key idea here, is I need to be able to start with, for example, the number 4, and I need to be able to church encode it in a way such that if I then beta reduce that down to some normal form, I take that and I run church to nat on it, well, now I had better get back 4. So I need to define the other side of this, this other function. So let's do church to nat, and this is going to be a church encoded. This is going to be a church encoded number, and I need to return a racket number. And so here's what the trick is. Okay, so what is the number n? It's a function that takes some f and then applies f n times to some x. Okay, so here's what we're going to do. We're going to recognize that we can make that function f be the racket function add 1, right? Because when I'm calling church to nat, I'm in racket, right? Church encoded number is like a bunch of lambdas. It's all in the lambda calculus. But here in church to nat, I'm executing in the context of like, racket land now. And so to do that, what I can do is I can call encoded number on add 1. And now this is a function that applies sort of add 1, add 1, add 1, add 1, add 1 as many times as the number n to some argument x. So it's like lambda x, add 1, x. That would be the encoding of 2. So now that's still not a racket number. That's, that's a lambda, right? Because if I take and I look at maybe this thing right here, well, now by calling encoded number on add 1, I've instantiated f, and the result is this lambda x. So it's like lambda x, add 1, add 1, add 1 of x. How do I get back to a number where I can make that x be 0? All right, so if I do this, and then I apply this on 0, then I get back the thing that I wanted. Okay, so let's do, I misspelled that. I want church encoded number. And this is because up here I've got the omega term, so let's comment that out. Okay, so here we go. Comment out those things too. And now let's do church to nat, and then let's do lambda f, lambda x, f, 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 x. There we go. And that is as expected. Okay. let's write this function. I'm just going to copy and paste it in from the notes. So this is this function nat to church. And so if I call nat to church on 4, I'll let you think about how this function works. It returns to me a, so this is not a racket lambda, right? Because if I had lambda x, then racket would say procedure, right? So racket will never actually show me the source for a lambda. This is not a racket lambda. This is actually just a quoted list, right? So there's nothing that prevents me on racket from doing like quote +1, 2, right? And this is in fact exactly how we implemented project 3. We were able to like, use quoted lists in racket to represent the syntax of the language. And in fact, that's one of the best things about racket, right? So how can I take nat to church? So this is a quoted list. If I want to turn that back into a racket lambda, I can actually use the function eval. And that gives me back now a racket lambda. And I can see that's like pound procedure. Okay, so that's racket's representation of a lambda. And now I should be able to take, so let's do eval and then nat arrow church of, let's say, 10,000. And then let's do church arrow nat. And I get 10,000. And see, it's a little bit slow, right? There's a lot of overhead in this encoding. If I make it 100,000, it's going to be doing a whole, like it's going to be doing hundreds of thousands of applications. In fact, it's going to run out of memory. Okay. But I think you get the idea. We can do the encoding. If you take my class CIS352, so we will discuss compilation into x86-64 code. Here we are compiling the number into the lambda calculus, but the lambda calculus doesn't have a space efficient representation of numbers, right? It doesn't actually have machine registers. It doesn't have primitive arithmetic baked into it. We're showing how in principle, with respect to Turing completeness, we can do the encoding of some number, right? But we're not actually saying that much about its asymptotic complexity or things like that. So we're just showing that it's possible to translate these things in, but it turns out the encoding is a ridiculously high overhead and not something we would actually want to use in practice. But still, it's an interesting one to learn, and it helps us understand that it's, even the lambda calculus is capable of expressing this. And then in a real implementation, you would just translate those aspects, not all the way down to the lambda calculus, right? But you would translate them down to, assembly level code at the machine level. Okay. So now we've talked about how to encode our first piece of data, which is numbers. Now I want to talk about how we can encode computations, right? So in racket, we can do add 1 of 10, and the result will be 11 as expected. And now we'd like to be able to systematically translate this kind of thing into the lambda calculus. And I already know how to systematically translate this one into the lambda calculus, right? I can do 3, 4, 5. And let's take those 5 and let's just paste them. There we go. There we go. So I already know how to take this thing and put it into the lambda calculus. That's 10. So now how do I implement add 1? Well, so that's a question. Let's come back to that. So we want an encoding, or I guess I should say implementation of add 1 such that this thing reduces to the encoding of 11. Okay, so how can we make that work out? So here's what we're going to do. So we're going to define it as follows. I'm going to say add 1 is going to be equal to lambda n. So n is going to be my argument. Okay, so that's some number. And here's what I'm going to do. I'm going to say lambda f, lambda x. And so when I call add 1, I'm going to apply it on some number. Like here, I'm applying it on this thing right here. This is the church encoded number 10, right? And that's going to be what is going to get filled in for n. But the result is going to be lambda f lambda x, right? Which is the start of a church encoded number, right? If you want to build a church encoded number, you can stub out lambda f lambda x. And now whatever I do under here, well, what I need to do now in this body is I need to call f n plus 1 times, right? So that's what I need to do in effect. I need to call f n plus 1 times applied on x. So now we need to think about how could we do that? So here's what we're going to do. We're going to start by calling n on f. What is that? That's a function that takes another function, right? So n is a function that takes f, and then is going to return a function that is basically f composed n times applied on some argument. And in this case, I'm going to want that argument to be x, the x that I started with. So that's going to get us basically f applied to n, or sorry, f applied n times on x. That would be basically the encoding of n. I'm going to use that as a subordinate result, which is now passed to f. And that's going to give me the whole last call. So this is going to be f applied n plus 1 times on x, right? Because this subordinate quantity that I've got highlighted here is f applied n times on x. Recall, this is just the definition of the number n, our encoding of the number n, at least, right? And so we're going to take that subordinate result, we're going to pass that to f, and that's going to be our final call. That's going to be that plus 1th call to f. All right, so that's how that works. And now let's test it out. All right, so I'm going to take this. I'm going to do church to nat. And I'm going to take this thing. And I'm hoping that this is 11. And it's not. So why is it not? It was broken because I had called this add1, and that just clashed with Racket's add1, which is giving some weird behavior. So I just renamed it to church add1. And once I do that, I get the result 11 as expected. Let's try to actually work through this definition. So let's look and see. So here's an example where we are applying add1 to 2. And the idea of the church encoding is that for an application, all we have to do is we just encode the left and the right side. All right. So in this case, at least if it's a single argument application, we encode the left and the right side. And we've just given the definition of add1 here. And this is the encoding of 2, right? So we've got f applied on x. And so let's just see how it works, right? So if I run the first reduction, I just keep reducing the term, and eventually I can see that by reducing the term some number of times, I now get one more call to f, right? So I get this outer call right here where I've got f applied on this inner result, and then this inner beta reduction eventually yields the result term here, this f applied on x. Okay, so at this point, hopefully each of the individual steps that we've done so far makes sense, right? So we've encoded natural numbers as data, and we've also encoded computations like add1. I mean, that's the only one so far. We're going to cover plus and times. So let's just kind of back up a little bit and make some points. So why are we doing the encoding? So we're doing the encoding to observe the fact that the lambda calculus is indeed Turing complete. And we're going to do that by taking a significant subset of Racket. In Project 4, it's quite a bit of stuff that we're going to cover. Most of the standard scheme, like letrec for recursive functions, multi-argument function calls, multi-argument lambdas, lists, booleans, and numbers are the 3 data types we're doing. So we're going to translate all of those systematically into the lambda calculus. And even though things like multi-argument lambdas might feel like relatively low-level features, you have to remember the lambda calculus is a tiny programming language, right? It's just, lambdas, abstractions, variables, and applications. And so, you know, encodings of certain things might feel relatively naive, like, for example, numbers. And in fact, as we'll see in the compilers class, if you take it, of course, we would want to translate operations over numbers when possible down to very efficient representations in the machine layer, right? And so are we interpreting like in project 3? No, we're actually compiling instead. So in this lecture, what we're doing is we're talking about how to systematically translate and encode each of these features so that at the end, you have a term that's fully in the lambda calculus. And now to execute the term, all you have to do is just beta. You know, you just do as much beta reduction as possible, at least, you know, according to some reduction strategy. Let's say if you're executing it in the context of another programming language like Racket. So, okay, let's talk about multi-argument functions now. So this is a trick that you're probably intuitively familiar with if you took our Haskell class here. So one fact about functional programming languages is that any argument of any function of multiple arguments, like here lambda x, y, z, apply x on z, anything like this can always be written as a sequence of lambdas. So we could say lambda x, return lambda y, return lambda z, whose body is then xz. And so that's the trick. If we have something like lambda x, y, z, and then we've got some body here. It doesn't really matter what it is, although we're going to have to encode that too. Then this is going to get translated to lambda x, lambda y, lambda z, and then whatever the encoding of e is, right? But if we, you know, if we do that, right? So we do this encoding where anytime we've got more than one argument, what we're going to do is we're going to just say, okay, it's going to be a function of one argument that then returns a function to the rest of the arguments, right? But when we do that encoding, we have to be careful to ensure that call sites, meaning calls to these functions. So for example, something like this, we have to ensure that this kind of thing also gets encoded as sort of this, right? Where we take our encoding here, we bind that to the first argument to apply it. That's going to be x. We take the result of that and apply it to 2, because that's our second argument. And now we're going to apply it to 3, because that's our third argument. And we have to do that because, you know, we're encoding the lambda, so we also have to encode the call, right? They have to match up. You can't have, you know, you can't curry all of the arguments. So now all of your lambdas are a single argument, but then also call them with 2 or 3 arguments, right? And so we have to be systematic about this encoding. So let's see an example of this. So let's say I've got a function like lambda x, y, return x plus y. And I'm saying that I could rewrite that. So let's make a call to f. So let's say it's f of 2, 3. And I'm saying I could rewrite that as the church encoded or curried version, lambda x, lambda y. And then here, this would have to be plus x, y, because everything has to be curried. It's going to turn out that plus is going to need to be curried too. We're going to see what how we can write plus in a second. And then if we have a call like f23, well, then we need to encode it like this. We apply f on that first argument. So we apply f on 2. That's going to plug in for x. That's going to give us this result of the lambda y, which is going to get plugged in. So y is going to get, 3 is going to get plugged in for y. All right, so there we go. And now it will work, except of course, if we really want to take this all the way down to the lambda calculus, we have to encode these things too. So I have to do something like lambda x, f applied on x. And this one is lambda x, f, x. So that's the idea. We can curry things, meaning that any function of multiple arguments can get desugared down into multiple functions. Also, just to handle the special case of the 0 argument lambda, we're just going to throw a bogus argument on it. So we're just going to say, okay, well, if you've got lambda of 0 arguments, that's just going to be lambda of underscore, where underscore is just like a bogus parameter. And then anytime we call a function of 0 arguments, so like if we see something like e surrounded in parentheses, right? So this is a call of a 0 argument function. We're going to add just the identity function as the argument, just to give something for that bogus argument to consume, right? It's going to be dropped, but we have to put something there. Okay. So that's how we can do multi-argument functions. And the reason we're covering that is because now we want to be able to encode things like plus of 3 and 4. And so how can we encode that? So we know how to encode 3 and 4, of course. We encode this as like lambda f, lambda x, x. And then we can encode 4. Let's just copy this one over and just add another call to f here. Okay, so there we go. And that's our encoding of this computation. And now the question is, how do we implement plus? Okay, so plus is going to be a function of 2 arguments. And what I mean by that is it's going to be a curried function. So we can define plus to be lambda. Let's do it n and k. So those are going to be our 2 arguments to plus. So n is the first argument to plus, k is the second argument to plus, and remember we're calling it in this curried fashion like we're doing up here. So in this application on 75, this would be applying. So here the encoding of 3 would get put in for n. This is a partially encoded term, I guess. So that's something that hopefully doesn't confuse you too much. Maybe it would be better to look at line 77. So here we've got this call to plus where this is n, and then this would be k. This is the encoding of 3. This is the encoding of 4. Okay, so that's n and k. And now this body, so let's do lambda f, lambda x, and this body needs to call f n plus k times on x. That's what we need to do. All right, so this is definitely a little bit of a mind bender. So how can we do it? So it turns out that what we're going to do is this. We're going to start out by calling f, or building this subresult, which is apply f n times on some argument, and we're going to apply that on x. We're then going to use this, which is f applied n times on x, and we're going to pass that as the argument to the result of calling k of f. So what is k of f? K of f is the function that takes something, in this case it's this subcomputation, which is f applied n times on x, right? It's going to take that subresult and it's going to apply f, in this case, k more times to it. And that's the beauty, right? In the sense that that's why we get these 2 arguments. This is what allows us to build plus, because instead of just starting from 0, here we can say, okay, well, k of f is a function that will apply f k times regardless of what you pass it. And so to build n plus k, what we can do is we can first apply f n times on x, and then we take that as a parameter and we pass it in to calling f k times on x. And that gives us the whole result. And I mean, this one I found when I first started, learning about this stuff, I found this one to be very, impressive. The fact that it was even possible. Let's call it church plus. Let's hit run. And then let's call this church plus, and it's all curried. And now we're going to get a procedure out. That's expected because it's a church encoded number. but we should be able to call church to nat on this thing. And what are we hoping is the result of that? Well, it's the church encoded version of 7, right? Because this is the encoding of 3, and then we've got the encoding of 4 here. So we get back 7 as expected. Okay, good. So that's what plus is. I will be a little bit more brief about handling times, but I'll just say, well, you know, now what is n times k? Well, it's a process that repeats the whole do fk times thing, right? So it repeats the process of doing fk times n times. All right, so you do fk times n times, and that gives you basically n times k. And so if I do something like this here, let's define it now. Church times is going to be this thing here. And then now let's change this to church times. And now we get 12, which is the encoding of, where we get the encoding of 12. I've called church to nat on it to be able to see it. And that's expected because this is 3 times 4, right? Okay. So now at this point, we can basically evaluate any arithmetic expression. All right. So if I have an expression like this, so if I've got something like this here, I can systematically encode it, right? So I can take this and I can say this is lambda f, lambda x, f applied on x. So that's that. And I will copy that over there because that's 1 as well. And then here I need to add one more call to f. And then I need to change these to church plus, and I need to change this to church times. And also I need to be a little bit careful because do I have multiple arguments here? Yeah, so here I'm calling church times and it needs to be curried. So let's do that. So I'll curry that. And then I've got this call here. And then has this been correctly curried? This seems like it has been correctly curried. And then I'm going to apply that on the result of calling this thing on it. So I guess we're hoping we get 3. And let's just call church to nat. And yes, we got 3. Great. Very cool. Okay, good. Worked out. Okay, so that's church encoded natural numbers. All right, we can do operations on church encoded natural numbers. We can translate operations that act over church encoded numbers. Let's move on to some other data types. So let's talk about the church encoding of booleans now. So first, we're going to assume things are well typed, as we did before. Like I said, our compilation into the lambda calculus is not injective, right? So there's plenty of lambda calculus terms that don't have any sensible meaning in our, in our encodings, right? So one of the next topics we're going to study in this class is going to be type systems and type theory. So we'll be studying that next week. And a big goal of type systems there are going to be able to use natural deduction and proof theory to ensure that we only have these well-typed operations. And so we reject these kind of bad programs. But for now, we're just going to say that if we use the encoding correctly, or if we use the encoding incorrectly, we're just going to say that's undefined behavior, right? So now let's talk about booleans. So in the lambda calculus, we can really only use a piece of data by calling it, right? Because at the end of the day, everything in the lambda calculus is a function, right? So the only way we can really interact with it is by calling it in some way. And for numbers, our encodings, the number n is encoded by using the function n times, right? We're applying the function n times in a row to something. And then our guarantee, if I tell you this is a church encoded number, Well, you know that it takes f and takes x and applies f in times to x. That's what it means to be a church encoded number. And if I give you something and I say, this is a church encoded number, it has to satisfy that behavior. It can't do anything else. And so let's think about what would the analogy be for a Boolean. So it turns out that the analogy would be something like a selector function. And what I mean by that is a function that takes, in a curried fashion, 2 arguments and either returns the first argument or returns the second argument. And it turns out we're actually going to want a slightly different encoding in Racket. We're actually going to want to have this encoding. And so we're going to encode. So we're going to say that the encoding of true is lambda true true, lambda false. And we're actually going to say it is invoke true as a 0 argument function. The reason for this is that Racket is a call by value language. And in a call by value language, we're going to want to support encoding if. So we're going to want to encode. So we're going to want to encode if E0, E1, E2 as E0 applied to E1, E2. And of course, that needs to be curried. So it's really going to be this right here. And in this situation, E0 is going to reduce to either true or false. It's not going to reduce to anything else because remember we said it was, we're going to assume it's well typed. And so if it's true, we want it to select the true branch and to start executing the true branch. If it's false, we want it to select the false branch and start executing the false branch. But when it's true, we don't want it to execute the false branch because that might be an error that we specifically want to avoid, right? Like maybe a division by 0 or something like that, or, non-termination, right? But because because Racket is a call by value language, it turns out that the encoding I sketch right here is not quite going to work. And so we're actually going to want to use this encoding. And so this encoding that I just sketched is basically the encoding of a bool is a 2-argument function which takes 2 callbacks. And I always pass them in the same order. Always passed in the same order. And the first callback, when true, is invoked when the Boolean is true. The second callback, when false, is invoked when the Boolean is false. If the first callback is invoked, the second is not, and vice versa. So basically, if I've ever got a Boolean value and I want to see if it's true or false, what I have to do is I have to pass 2 callbacks. And those callbacks, they're both 0 argument callbacks, right? The reason is that if I put a lambda in front of something in a call by value language, no reduction is going to happen under it, right? And so, okay, so now I'm going to define church true is going to be lambda when true, and then it's going to be lambda when false, because when I show it here in these notes, I'm assuming that you are also encoding it using the encodings we've described, right? So lambda when false, and then I've got when true, and this is when true called on 0 arguments. So I'm going to call it with lambda xx because that's how I encode a call to a 0 argument function in the way that we're doing things. Church false, and then I've got lambda when false. Or sorry, no, they always have to be in the same order. That was a mistake on my part. When false, and then this is going to be when false, lambda XX. Okay. And these are going to be my encodings. And so if I want to see whether a value is true or false, what I have to do is I have to put, I have to pass these two functions to it. So for example, if I pass church true and I say, this has to be a bogus argument here. And let's say I'm going to display len, the value is true. And I'm going to take that and I'm going to pass a second curried argument to it. Notice I'm currying it by putting these calls here. And then this is a second one. So here we go. Display len, the value is false. And I get back the value is true. But if I change that to church false, well, now I can see the value is false. Okay. And of course, just encoding the values true and false is a little silly, because if you know that it's true, or if you know that it's false, you would never actually ask whether it's true or false, would you? Right? You would just know. So it gets more interesting when we realize that we can also start to encode computations or operations over booleans. And so one of the first operations we can encode over booleans is not. So logical not should take, it takes some church encoded boolean, and if that church encoded boolean is true, then it should return the church encoded boolean of false. If that church encoded boolean is false, then this should return, or not of church encoded boolean should return the church encoding of true. So how can we make that happen? Well, we need to be able to see, is church encoded boolean true or false? And it turns out, of course, like I was saying, the way we have to interact with church encoded boolean is by calling it, specifically calling it with two arguments, which are both callbacks, which just mean a function that's going to get called under some circumstances. That's what the word callback means. It comes from like GUI programming, right? If you've ever done any programming over a GUI, we frequently use that term callbacks in that sort of settings, and some other settings as well. But just a function that's going to be called under some circumstances. So here's what I'm going to do. I'm going to say, we're going to call church encoded. My dog's tearing up the little dog mat back there. Here we go. Church encoded boolean of, and here's what we're going to do. We're going to pass it. So this is a callback that's going to get triggered when it's actually true. And so when this callback occurs, so I'm going to name this, I'm a bogus but true. So this is a bogus argument that's just happening just due to the encoding. And my job here is that, well, I know that I would only be, the first argument to church encoded boolean would only be triggered in the event that church encoded boolean ultimately was true. And so now here, I'm going to return the church encoding of false. And then my second argument is going to be another callback that is going to be I'm bogus but false. And here I'm going to return church true, because I know that this lambda only got invoked if this church encoded boolean was false. That's how our encoding works. The encoding for a boolean is you always have to call me with two arguments, curried fashion. If I'm true, I'm going to call your first argument, but not your second. If I'm false, I'm going to call your second argument, but not the first. All right, so we're going to define not by saying, okay, well, you give me some church encoded boolean. I'll call that church encoded boolean. My callback that I'm going to pass for the when true case is going to return false, and the callback I'm going to pass for the when false case is going to return true. And so let's write a function church to racket. Let's do to racket bool. I'll just do church to bool, and it's going to be a church encoded bool. And so here's what we're going to do. I'm going to call church encoded bool, and that's a church encoded bool, and I'm trying to turn it into a racket. Give back either true or false. So the first argument is going to return, so this gets invoked when church encoded bool is true. And now this is going to get invoked when it is false. And that'll help me be able to do some testing a little bit easier. So now I can just say church to bool of, and let's call this church not. And then let's do church not of church not of church not of church not of church false. And that should be false because we do not, that cancels, and then not. And so we should get back false. Okay, so here we go. False is our result. All right. So, okay, we got the result as expected. We did a bunch of calls to church not, and we chained them all up. So that's how we do the encoding there. Let's see. So now that we have these, so now that I have church encoded booleans, I can also church encode if, and I'm using the term church encoding in a fairly loose way. I'm actually using a variety of different encodings like Bucaderi and Bohm encodings in this class, but I'm calling them church encodings in this lecture. So that's the name we'll go with. And so now that I have church encoded booleans, I can encode if. So if of E0, E1, E2 compiles to, or encodes to, I guess I should say, E0 applied to the encoding of lambda of 0 arguments, E1, and lambda of 0 arguments, E2. And in this lecture, I'm assuming that you're doing the encoding of these things so that you can get the full encoding. So this is really like this. And then we've got, these both have a bogus argument attached to them to make them in the lambda calculus. And that's what the encoding is going to be. And this is going to see by wrapping it in a lambda, when I execute this in Racket now, which is a call by value language, if I have something like this, so let's say I do, so let's say I wanted to translate if of false, and then this is going to be the omega term. Otherwise, let's say 1. And we know that this should reduce to 1, right? And so I'm just saying that the encoding should be church false. And now I'm going to pass in lambda of 0 arguments, and the true branch will be the encoding of false. No, I messed it up. In this case, I just want the omega term as the first argument, and then I pass 1 as the second argument. So that's just lambda f, lambda x, f applied on x. Comment this out. And this should yield the church encoding of 1, except, no, I need to make sure these things are surrounded in a lambda of 0, of 1 argument. Keep doing that. So here we go. We get back a procedure, and we had better be able to turn this into 1 by doing church to nat. And as expected, the result of the encoding of the whole thing, so the encoding of this computation here, we encoded the if by doing just this encoding we're showing here, where we're taking E0 and then we apply it. The first argument is just this. In this case, I wrote D for dummy underscore. So it's a bogus argument. And then the second argument in curried fashion is the false branch. And so we need to do that in Racket because if I had just this and I didn't have the lambdas, well, now all of a sudden this wouldn't terminate anymore because now I've got the omega term right here. And because Racket is called by value, I need the omega term. So this is the way that I did this encoding and has set it up for this class is assuming that we're, it's partially because we're using Racket. And so if we were doing, Haskell, for example, the encoding might look a little bit different. And and or can just be encoded as strings of ifs. So you've probably already learned about that, right? So and can say if of E0, then E1, otherwise false. And same thing with sort of vice versa for or. If E0, then the whole thing is true, otherwise test E1. Okay. So now we've talked about the encoding of numbers. We've talked about the encoding of booleans. We've talked about the encoding of operations over numbers, plus, times, add one. We've talked about operations over booleans, so not, this example of that. So now we need to talk about our most complex piece of data yet. And so how do we encode lists? Okay, so how do we encode lists? So here's how we're going to do it. So remember back when we were encoding booleans, we said a boolean is basically a 2-argument function. Both of those callbacks are going to be 0-argument callbacks. If you called the first callback, you know it's true. If you call the second callback, you know it's false. If you know it's false, you know it's not true. If you know it's true, you know it's not false. But those callbacks, they were all just bogus arguments, right? So there wasn't actually anything useful in them. We can support more complex data types like lists by changing that up a little bit. And so, well, first, what is a list? So what is a list? So it's an inductive algebraic data type that has 2 constructors. So it's an algebraic. So it's an inductive type with 2 constructors. Either it's empty, it's either the empty list, or it's a cons cell, or it's cons of x and some list L, where x is the first element and L is a list. And so here's how we're going to support that. We're going to say that we will encode every list as a 2-argument function that's going to be when cons, when null, and then if it's cons, we invoke when cons with the car and cdr, or the first and rest, right? So the left side, so a cons cell contains 2 things. It contains a first element and a rest of the list, or it contains a car and a cdr, right? A cons cell is a pair where the second element is a list. So if it's a cons cell, we invoke when cons. A cons cell is carrying around both that car and the cdr value, so we pass the car and the cdr to when cons. If it's null, then we invoke when null, or when empty, with 0 arguments. All right, so if it's null, then we invoke when null with 0 arguments. The fact that it's null tells us that it's not cons, but it doesn't tell us anything else, right? We don't know anything other than the fact that it's null. The empty list doesn't really carry any information. It just tells us, well, you're not a cons cell, you're definitely null, and you can use that to determine the base case. Okay, so that's how it's going to work. And if we take that point of view, then it turns out we can define, we can define the empty list in the following way. So we can say it's when cons, and remember these need to be curried. So here we're going to say it's when cons, and then we're going to say it's when null. And we are going to invoke when null on the empty, on just a bogus argument. And so it's going to be the identity function here. So that's what the empty list is. Okay. What about cons? Well, cons is a 2-argument function. It's going to take A and it's going to take B, or I guess I should say the car and the cooter, right? Because every cons cell has a first and a rest, or car and a cooter. And what we're going to do is we're going to return a function that is lambda when cons, right? Because every list has to have this form where it takes when cons and when null, just like how booleans are always 2-argument functions that's like when true, when false. And now our job is going to be to call when cons on the car is the first argument and the cooter is the second argument. So that's how we're going to make cons cells, and I guess we should call this church cons. And so yeah, that's how I can make it work. I can define null-ha. So for example, I can define null-ha, church null-ha, with some church encoded list. And here's what I'm going to do. I'm going to call church encoded list with 2 arguments. The first argument is going to get called if it's a cons cell, right? So that's the when cons. So it's going to get passed the car, the cooter. And now what do I do? Well, I'm trying to tell you if it's null or not. Now, I just saw that it was a cons cell. So it can't be null, right? Because a cons cell is never null, right? If the list is a cons cell, then it's not the empty list. And so here I'm going to return church of false. And then because I have to call church encoded list as a 2-argument function, the second argument I'm going to pass in is just this bogus argument. This is called when church encoded list is the empty list. And that's what I'm looking for. I'm church null-ha. If I see the empty list, then I know that I need to return church true. Okay. So here, let's take that out. So there we go. So that's my result. So now let's do church null of empty list. And then we need to convert that to racket by calling church to bool. And this is in fact true, because the empty list is in fact null-ha. Meanwhile, if I call church to bool-ha on the result of church cons, and then let's do the encoding of 1. So this is cons of 1, and I'm going to cons up that with the empty list. So this is empty list. This is basically the list containing 1, right? And I'm calling church to bool on that. And this had better be false, because this is not the empty list. Okay, so something broke. All right, but if instead I do church null-ha of the application of cons of 1, so the encoding of 1, to the empty list, then I get back false, as expected. Okay, so then how would we write car? So how would I define car? So that is a function that takes a list, or I guess I should say a church encoded list. And it's going to call church encoded list, and my first callback is going to say the car and the cooter, and I want to return the car. And now I need to pass another argument, which is something here, and this is something that just should be an error. So I should get like you know, here I should just raise some sort of an error. I shouldn't get here, right? So I should assert false. Okay, so now if I do, if I apply car on the application of, so if I apply car to this thing, then I should get back the number 1. And if I do church to nat, is it church arrow nat? Yes, it is. If I do church arrow nat to this, then I get 1. Okay, so I think that's where I'm going to leave it tonight. I will continue, and we'll talk on Thursday about letrec, which is how we get recursive functions. And to do that, we need either the U combinator or the Y combinator. I discussed both, and so that will be next lecture. All right, thanks everyone.